All right, so let's get to it. We left off with the example of having 10 randomly selected people from a normally distributed population, and we wanted to know what's the probability, given the mean and given the standard deviation, that they have a mean for them of 98.2 degrees. So we are going to use what's called the central limit theorem, which is going to be a lot of words, but pretty straightforward as far as how we do it. What's going to happen is if you've got one of these two conditions, and for us, we do have one of those conditions because, well, I assume the overall population is normally distributed, so we do have number one there. The fact that we're getting 10 people in our sample is okay because we've hit this first condition. You don't need both, just one or the other. And because we have hit one of those conditions, we're going to be able to use an adjusted z-score. Right? Normally, the z-score is x minus mu over sigma. Now we're going to do an adjusted z-score for a sample. So I've got 10 people here. X bar is the mean of my sample. Our new mu, well, that's actually just the old mu. We're going to be able to use the mean of sample means, which of course is just the population mean. Honestly, that was the big point of the previous section, where if you have a whole bunch of samples and you average together all those samples, the mean of those sample statistics becomes or approaches the population parameter. So why we get a new symbol here, I don't know. That's something that statisticians decided to do. But really, it's the same mean. You get to use population mean here. And you're able to use that because of the previous section, what we did there. So no change to mu. What does change, however, is sigma. Whenever you're doing a sample, not just one person, but a sample, you adjust your standard deviation value. And the way you adjust it, this is terribly important, is you take the original standard deviation and divide it by the square root of the number of people in your sample, or the number of values in your sample. So for us here, our mean is 98.6. Our standard deviation for the whole population is 0.62. And now we're going to use the central limit theorem to find our adjusted z-score. Of course, x bar is 98.2 because that's what we're trying to find out about. Mu is, well, still mu. That doesn't change, thanks 6.3 section. We do an adjusted value for standard deviation. We're going to take our original population parameter for standard deviation, and we will divide that by the square root of 10 because there were 10 people in our sample. And that comes about to be about 0.2 degrees Fahrenheit. So now, under our adjusted values, under our central limit theorem, we get an adjusted z-score of about -2. And then we look that up on our z table, and we've got a probability now of having a mean for all 10 people combined to be about 2%. And I want you to compare that to the 25% we had for one person, or the 1 in a million chance that we had for having all 10 people. It's about 2% for the mean, which isn't super duper rare, but it is still rare. So let me tell you this then, because this is not something you have to understand entirely right yet, but it is something we're going to have to talk about by the end of the semester. Whenever you got something that's significantly rare, and remember this, significantly rare is either cumulative probability below 5% or above 95%, or the result is more than 2 standard deviations away from the mean. I want you to look at this. We were more than 2 standard deviations away from the mean. -2.04 was our adjusted z-score. So this result was significantly rare. Now, what we're going to get into with hypothesis testing is that means that either we just had something weird happen, or more likely than not, one of our underlying assumptions was incorrect. So it could be that this 98.6 degree mean temperature is too high, or it could mean that our standard deviation was too low. Maybe they're both a little wrong. We don't know how wrong it is, but we've got some evidence now to say it's not all right.